Hello everyone, my name is Yuefeng. In this talk, Haoyu and I will talk about the primary server training in TensorFlow 2 on behalf of multiple developers working on it. This talk will cover primary server training and evaluation overview, single client architecture for TensorFlow 2 primary server training, schedule join API for this single client architecture, inline evaluation, and variable sharding. After my part, Haoyu will talk more about how primary server training is implemented from runtime's perspective, how work-fault tolerance works in a single client architecture, and how we tune our performance on a synthetic recommendation model. First, what is primary server training? In short, it is a common data parallel approach to scale up model training on multiple machines. In this approach, variables are stored on primary servers shared by all workers, and most of the computation happens on workers. In each training step, workers pull latest variable values from primary servers. They run forward backward passes with their own training data, and they send back gradients to primary servers. Each worker completes a step independently, and they update variables on primary servers independently. So this is why it is also called asynchronous training. It is scalable because the workers don't have to wait for each other. And also because of this, it can tolerate some work failure. But there's a stale gradient problem. So what is stale gradient problem? So let's say one worker puts variables at the time A, and it sends back gradients at time B. But during time A and B, this variable may have already been updated by other workers. And if we have more workers, we're going to have more stale gradients. Stale gradient problems may hurt model quality, and different models may have different sensitivity to this problem. One ongoing research that is worth mentioning in this talk is the adaptive learning rate method. The main idea is to discount learning rate based on the staleness of gradients, and the goal is to get close to synchronous training. This diagram shows some preliminary results on recent CIFA with 50 workers. The x-axis is the number of epochs, and the y-axis is the accuracy. The blue curve represents the standard asynchronous training algorithm, while the yellow curve and the red curve represent the adaptive learning rate algorithm. We can see that the training with this algorithm has a more smooth accuracy curve and converges to state-of-the-art much faster in terms of the number of epochs. On the other hand, synchronous primary server training is also possible. It can overcome the stale gradients problem. In TensorFlow 1, we implement the synchronous primary server training using sync replicas optimizer. It creates one conditional accumulator per variable, and it will not aggregate and apply gradients before it accumulates k gradients. This optimizer uses a queue as a barrier to coordinate workers, but it may hang in the case of task preemption. One nice thing about this optimizer is it can have some backup workers, so it can tolerate some worker failure. But the redundant gradients from the same step will be discarded. And overall, it's very complicated to implement such synchronous primary server training algorithm in TensorFlow 1. For the evaluation part in TensorFlow 1 primary server training, we use a dedicated machine to do evaluation. So this dedicated machine keeps checking checkpoints written by the chief worker, loads the latest checkpoint, and runs evaluation against that checkpoint. But the multi-worker evaluation is a top ask from our users. The problems with this evaluator is it cannot hold large variables. It cannot hold those large models, and it's slow with large evaluation datasets, and it's also slow with loading large checkpoints. It's difficult to use the evaluation results for early stopping on the training side, and it heavily relies on checkpoints. It's a waste of resources if the chief checkpoints not often, and it may miss checkpoints if the chief checkpoints too often. And it may also need some special casing for deployment, which has brought us some trouble in the past. So in TensorFlow 2, we use a different architecture to do primary server training. Let's first talk about the multi-client setup in TensorFlow 1. So in TensorFlow 1, we use a multi-client setup where each worker runs a copy of the user program and coordinates its own training. Each worker also creates variables and there's some magic happening on prime servers to map variables created by different workers to the same underlying storage. There are problems with this multi-client setup. First, it's difficult to coordinate workers. As we have seen, it's complicated to implement the synchronous prime server training, and it's difficult to make it correct. And it's also difficult to do early stopping for training based on evaluation results. Next, it's difficult to achieve consensus among workers because there are no single source of truth. Let's take the TF1 prime server training, for example. If two workers create the same variable on different prime servers, then there's a problem. What we want is to create the same variable on same prime servers so that all workers can share all these variables. And because of with this issue, there are probably no errors reported to users, but users may notice that their model cannot converge to good accuracy, and it's very difficult to track down the issue to the inconsistency between workers. The multi-client setup also has a less intuitive programming model, since beginners may have a hard time understanding this MPR-like programming model. It makes the deployment and testing a bit less flexible. We cannot run it in Colab, and there's even no testing for distributed estimator in TensorFlow 1. If you have experience with multi-worker mirror strategy, which is multi-client as well, you probably have run into hanging issues in the past. Most of the issues are related to the inconsistency between workers. For example, different workers may create different nickel ops in different order, leading to the cluster to hang. In TensorFlow 2, we recommend a single client setup where workers and the prime servers runs TensorFlow servers. They just sit there and wait for requests from the coordinator. The coordinator runs a copy of the user program. It creates resources on prime servers and the workers. It dispatch training work to those workers, coordinates the training, and it deals with the task failure of workers and prime servers. There are several benefits of the single client setup. First, it is easy to coordinate workers. As we have seen, it's complicated to implement synchronous prime server training in TensorFlow 1, but we can implement an approximately synchronous training prime server training algorithm with these APIs that I will introduce later. We can also easily implement early stopping with inline evaluation, which I will introduce as well. It is easy to have worker consensus since there's only one source of truth. With that, we can avoid a lot of bugs because of inconsistencies between workers. The single client setup can also allow a more intuitive programming model, which I will talk about in detail in a moment. It's also easy and flexible to deploy a single client cluster because we can create a bunch of TensorFlow servers in advance on Borg and connect to them from a laptop or from a Colab. We can also run the whole cluster within a single process, which makes the testing very easy. There are also problems with the single client setup, which I will not avoid talking about them. The coordinator may become a bottleneck when scaling up the number of workers, but this is probably not a big deal for prime server training because we used to see that when we scale up the number of workers, prime servers become a bottleneck first. Because if you think about it, you will notice that a variable is also required by all workers in a single step, which has very similar patterns with the coordinator. There are also multiple ways to mitigate it. For example, you can have multiple in-flight requests to mitigate the latency issue. The coordinator will become a single point of failure, but training cannot continue without a prime server going down as well. And it's not impossible to mitigate it. Another limitation is current TensorFlow only supports remote TF function. It cannot ship any arbitrary Python function to remote workers. So let's take a look at the APIs for this single client architecture. The most important APIs are schedule join primitives. They provide a thread pool-like programming model. The schedule method schedule a function to one available worker in the pool. It actually just puts the function in a queue and returns a future-like object immediately. The join method will block until all scheduled functions are done. These scheduled join APIs are very easy for implementing load balancing between workers, fault tolerance, and even dynamic scaling in the future. Let's take the fault tolerance as an example. If one worker gets preempted, the coordinator will notice it by seeing an interrupted function. The coordinator will then put back this function to the queue and retry it on another available worker. The coordinator will wait for recovery of this worker in a separate thread, and once this worker is back, the coordinator will rebuild the resources on this worker and continue dispatching functions to this worker. Because of this fault tolerance mechanism, the function execution has at least once guarantee, meaning that a scheduled function will be executed at least once. The schedule join APIs are contained by this cluster coordinator class. It had to work in conjunction with TF.distributor strategy at this moment. The TF.distributor strategy defines the training loop, and it tells class coordinator what's the requirement for scheduling and what's the requirement for fault tolerance. The class coordinator also has a method to create resources for each worker. This create per worker dataset method will create one dataset per worker. What is more important is that the coordinator will rebuild the resources on workers when workers recover from preemption. The coordinator will just invoke the dataset function again to recreate the datasets on recovered workers. One thing to note here is that with the current implementation, the coordinator doesn't provide visitation guarantees on datasets. This is because the schedule method assumes that workers are equivalent so that it can schedule to one available worker. And as a result, each worker may run an indeterministic number of steps. Actually, this create per worker dataset method creates the same dataset on different workers, except that they may be shuffled differently on different workers. Estimator doesn't provide visitation guarantees for training datasets as well. So in the short term, this is probably not a huge problem. Let's see how the APIs are used. Here's a short example for custom training loop with mirror strategy. We first create a strategy, create all of those model objects on the strategy scope, create a dataset using the strategy method, create a step function, which contains multiple replicas. Then we invoke the step function multiple times. Now here is the training loop with prime server strategy and a class coordinator. We try to have minimum changes for users when they switch between strategies. We still use a distribution strategy to define the training loop, and we use a class coordinator to dispatch this training work to remote workers. We first, as highlighted here, we first create a strategy. We create a class coordinator and pass in the strategy object. Then we create one dataset per worker using this create per worker dataset method. We define the training loop in the same way with other strategies. After that, we use the coordinator to dispatch step function to remote workers. We call join at epoch boundaries so that we can checkpoint, write summaries, or print metric values. There are limitations with the current implementation of the API. There's no visitation guarantee for training dataset, as I mentioned. And another issue is that primary server preemption will lead to an unavailable error on the coordinator. And the coordinator will catch this error and exit with a special error code to signal bug to restart the coordinator without counting toward task failure. After restart, the coordinator will connect to those workers and the primary servers again, create resources, and continue dispatching functions. There may also be performance issues. Since our initial implementation is Python-based, and we create a lot of threads in Python, there may be threading overhead and gear overhead. So we are trying to reduce this overhead by moving the implementation to the runtime. Furthermore, if the latency between the coordinator and the workers is high, we need to mitigate it by issuing multiple steps in a single RPC call. In later slides, Haoyu will introduce ways to achieve optimal performance, even with these limitations. The last limitation is it can only dispatch TF function, which we may or may not realize in the future. Let's see the evaluation for TensorFlow 2 primary server training. We can still use sidecar evaluation, which we have seen in TensorFlow 1 primary server training, that we use a dedicated machine to do evaluation. Inline evaluation is made possible by our single client setup. So the inline evaluation refers to run evaluation on the coordinator or run evaluation on the same worker pool. And we can alternate between training and evaluation. This is very consistent with Keras APIs. There are benefits of inline evaluation. We don't need a special evaluator job. We are able to use evaluation results to early stopping for training. And we can evaluate large models because we have multiple machines, multiple primary servers. And it's faster to evaluate with large data sets, also because we have multiple machines. There are some limitations with inline evaluation. If we use schedule join to implement a multi-worker evaluation, but this is not a problem if you just run evaluation on the coordinator. So the problem with using schedule join for multi-worker inline evaluation is there's no verification guarantee, as I mentioned before. But the verification guarantee may be very desirable for evaluation. And the possible solution here are to either use TF.data service or we create many virtual shards from the evaluation datasets and schedule an entire virtual shard to a remote worker. Another limitation is that schedule join only provides at least once guarantee, but we would like to have it exactly once guarantee for evaluation. We would like to evaluate each evaluation example only once. And the possible solution is to get the evaluation results from the return value of functions, and we only schedule functions that don't have any side effect. The last but not least part is variable sharding. Variable sharding refers to splitting a variable into multiple shards and putting them on different primary servers. Variable sharding is important for load balancing between workers to achieve larger effective bandwidth of a training cluster. Variables that are sharded will become sharded variables, which is just a container holding all shards of a variable. Sharded variable can work efficiently with tf.n.embedding lookup. It does embedding lookup on primary servers in parallel, and it only needs to transfer back embedding slices to workers. The gradient update can also happen in parallel, and only relevant slices are touched. Sharded variable can be converted to a tensor by concatenation, so that it can work with most of TensorFlow libraries seamlessly. There are also other forms of model parallelism related to variable sharding that don't require concatenating all of the shards. For example, we can do sharded matrix multiplication on primary servers and then concatenate the results on workers, as opposed to concatenating all the shards on workers first, then do matrix multiplication. Here's some ongoing and future work. The list is not exhaustive. The first item is to integrate primary server training with Keras compile fit. We would like to support handling primary server failure without restarting the coordinator. We would like to have a packed representation for sharded variables. We would like to improve the performance of the coordinator. We would like to provide canonical workflows for inline evaluation if this becomes a popular feature request. We would also like to support the synchronous primary server training and multiple GPUs per worker. What is more important is that we want your help and feedback if you are interested in any of these features. So next, I'm going to hand it over to Haoyu, who is going to talk about how primary server training is implemented from runtime's perspective, the performance and scalability.
All right, thank you, Yuefeng. I'm Haoyu from the TensorFlow runtime team. Next, I'll be talking about the PS strategies implementation inside the TensorFlow Eagle runtime, basically how it's partitioning the model to the workers and parameter servers and using the distributed multi-device functions to drive its execution. I will then show some experiment results of the performance in large-scale training compared with the TensorFlow V1 estimator. So we will also see some of the problems we've encountered, and I will briefly talk about the solutions to fix those problems. So one major advantage of using parameter server training is to support fault tolerance so that the jobs can run on preemptible resources at large scale. So I will show some experiment results for running the jobs on preemptible clusters. And finally, I will briefly talk about the multi-worker test bed we've set up to run performance, convergence, and fault tolerance tests, and also its integration with the MLCompass framework. First, let's look at how the PS training interacts with the eager runtime. So as Yuefeng previously mentioned, we design and implement the single client parameter server training. So here we have one client coordinates a cluster of workers and parameter server instances to perform the training. User code is deployed on the coordinator to drive the model execution, just like the one shown here on the bottom left corner. All the workers and parameter server instances are just running the standard TensorFlow server binaries. So users first define their model as a TF function, and then call the schedule API to dispatch the model functions to these workers. And as previously mentioned, the schedule API is asynchronous, which means that the functions will only be queued up on the coordinator side, and the schedule call will return the control back to user's code immediately. Here we already have several functions queued up on the coordinator side, and a background thread pool will dispatch those functions to workers. Each function is actually a multi-device function or multi-worker function that spans one worker and multiple parameter server instances to read and update the model variables. The function gets instantiated and partitioned on the workers and further executed on both the workers and parameter servers. The function return status and return values will then be sent back to the coordinator. This way, the PS training achieves both model and data parallelism, with model partitioned on multiple parameter server tasks and the training performed on multiple data batches on multiple worker tasks concurrently. Let's further zoom into these distributed functions and see how they get partitioned and executed on different tasks. Here I'm showing an example of 2 workers and 2 parameter servers. We have a very simple model with only 2 variables, v1 that's placed on v0 placed on PS0 and v1 placed on PS1. The coordinator launches a model computation function replicated on these 2 workers. In each training step, they both read the latest version of the variables and perform model computation to get the gradients, and finally, the gradients are updated on those variables. Since these variables are actually located on remote work tasks of different hosts, the function will need to be instantiated and partitioned as distributed functions, like is shown in this graph. So here it shows that the function on worker 0 gets partitioned as 3 component functions. So one of them is located locally on worker 0, and others are located remotely on PS0 and PS1, respectively. The local subfunction on worker 0 is mainly responsible for model computation, and the one on PS are for sending variables and aggregating the gradients. The nodes in different functions are connected by send and receive ops. And the arrows here in this graph indicate the data dependencies, and I'm using the dashed arrows for remote data dependencies. The same partitioning logic also applies to the remote function that's running on worker 1, which will be executed independently from the function that's executed on worker 0. Note that here the function graphs are just for illustrative purposes, and they're not the actual definition of function graphs. The real graphs will involve several variable read and write ops and some remote copies, which we actually omitted here for simplicity. Next, I will switch to talk more about the performance measurement of the PS strategy. Our performance is measured based on training a large embedding model with parameter servers. So this kind of model represents a very common production use case for parameter servers because the embedding model typically has a very large vocabulary size and embedding layer that cannot fit in one device. So they require to be partitioned among multiple parameter servers to achieve model parallelism. The embedding model we tested here has 2 embedding layers. That's a user and item embedding, and also then followed by 3 fully connected dense layers. There are a total number of more than 1 billion trainable parameters in this model. So we measure its performance with different cluster sizes and compare them with the estimator. Here is a preliminary result. So we have the number of workers growing from 10 to 320 on the x-axis, and we have the measured throughput in terms of global steps per second on the y-axis. Note that the x-axis is actually in log scale, and we also increase the number of parameter server instances proportionally to keep the ratio of worker to PS at 5:1. According to the TFX team, this ratio is a production practice by default. So we first look at the plot with only two series of numbers measured from running the estimator and the vanilla PS strategy. We can see that with this vanilla PS strategy deployment, it does not perform as good as estimator after the cluster scales to more than 80 workers, and the performance gap further increases with larger cluster sizes. So this is mainly due to two reasons. First of all, the estimator runs the client code locally on each worker, but the PS strategy actually needs to dispatch a function from a remote coordinator. So the network round-trip time is actually exposed as part of your step time. And second, since the current coordinator implementation creates one Python thread per worker, there will be more and more Python GIL overhead in larger clusters due to the context switching overhead on the coordinator. And this GIL overhead can actually be quite large with more and more workers. So what we can do is to use a technique we call multi-step packing to mitigate this problem. So in the user's custom training loop code, we can pack multiple training steps in each function as opposed to just running one step per function. We can see that if we just pack 5 steps in each function, the PS strategy can achieve the same performance as estimator for this specific model. And to be more concrete, the code here on the right-hand side implement multi-step packing with an inner loop to pack n model training steps inside each TF function. And as we saw from the previous slide, using the number of n equals 5 here is enough to achieve the same performance as estimator in this specific workload. And note that we're not the first one to introduce this worker training loop concept. This is actually also in the TPU model performance guide as a performance knob that users can tune in their model. So we can further look into the performance impact of multi-step packing by inspecting the profiles we grabbed from the workers. So the one on the top is a training without multi-step packing, and the one on the bottom is training with multi-step packing. And each small block here can be roughly treated as a time it takes to run one function on a worker. There are actually many other small ops here in the thread pool below, but we're not showing them here due to the space constraint. We can see that the gap time between steps is roughly the same for both profiles. So it's actually 5 to 10 milliseconds in this case. This includes the network round-trip time between the coordinator and the workers, as well as the coordinator Python overhead waiting for the GIL. So with multi-step packing, the amortized gap time per training step will be much less, so the training throughput can be improved a lot. To demonstrate the improvement even further, in the next set of experiments, we slightly change the model to make it smaller and less computation intensive. So we do so by reducing the number of dense layers from 3 layers to only 1 layer. This way, each model step can be finished in a much shorter time on the worker side. Since we make the model smaller, we also need to change the worker to PS ratio from the original 5:1 ratio down to 2:1, so that the PS can have more computation capacity to accommodate the workers. So in the performance experiment here, we vary the number of workers from 8 to 256 on the x-axis, and we measure the performance on the y-axis. We can see that with 10 or more steps packed inside each function, the performance is consistently higher than estimator. And note that this model is intentionally designed to have a much larger throughput at thousands of steps per second, just to amplify the multi-step packing performance improvement. And typically in production models, we usually see only a few hundred steps per second, which is much less than the performance here. So packing 5 to 10 steps in each function should be more than enough. While multi-step packing can normally improve the performance, there are also some subtle issues users need to be aware of when doing this. First of all, it actually increases the cost of worker failure recovery. The basic unit for the coordinator to retry is at the function level, And recall that the user schedules a lot of functions inside the coordinator asynchronously, and each function can carry only one return status or return value. So if the function fails, the coordinator will think that all steps in that function has already failed. So it needs to rerun all the steps in that function on a different worker, even if some of the steps might have already finished successfully. And second, the coordinator has less fine granularity in controlling the training step and getting the return values and metrics. And finally, with the custom training loop API, multi-step packing actually requires user code changes, so it's not transparent to users. But on the positive side, multi-step packing effectively reduces the coordinator overhead, and we've yet to see a use case where multi-step packing can negatively affect the performance. And in the future, when the PS strategy has native carry support with a compound fit API, this multi-step packing can also be hidden inside the library. But one thing to reiterate, as Yuefeng mentioned before, is that multi-step packing is a solution to overcome the current limitation of our implementation. And we do plan to keep improving the efficiency of the coordinator with potentially like moving some of the user space threads into the runtime. So when we achieve that, users will no longer need to worry about the thread contention or tuning this multi-step packing knobs. Next, I will briefly talk about the results from large-scale fault tolerance testing. So from this, we can see that nearly half of the brain jobs actually fail due to preemptions. And this is even more likely to happen when users are running the jobs on a cluster of hundreds or thousands of preemptible machines. Without fault tolerance support, worker failures can cause either the job to hang forever or it will have to frequently restart from a checkpoint with a huge waste of idle resources during that period of time. For the TF2 parameter server training to be ready for production use cases, we will need to achieve the following. First of all, the failure handling must be reliable and fast. The failed workers should not prevent other healthy workers in the cluster from making continued training progress. The second requirement is that the failure recovery must be efficient. So when new resources or workers join the pool, the strategy and the runtime should work together to help the user's code automatically rebuild the resources and continue to run the model. And the final requirement is that the model should achieve at least the same level of scalability and performance compared to the TensorFlow V1 estimator-based implementation. And in TensorFlow 2, PS training and the eager runtime work together to handle worker failures. We create multiple threads dispatching functions on remote workers, and if the function returns with an unavailable error indicating that the remote worker has failed, it will signal a background thread to update server def, which updates the cluster view on all the participating tasks with a new cluster membership. Other workers at the same time can keep handling the scheduled function execution request from the coordinator without being interrupted. And if the failure happens to the parameter server, which is not shown on the slide, the coordinator will reinitialize the cluster and reload the model from the latest checkpoint. And this way, we can handle both worker and parameter server failures. So we have tested the parameter server training extensively with 3 goals in mind. The first one is large scale. According to the TFX team, 200 worker is about the average size of production jobs, and 1,000 worker is over 99th percentile of the deployed production jobs. So we need to make sure that the jobs can run smoothly at both these different scales. And the second goal is low priority resources. So production jobs using batch resources often encounter and must tolerate both PS and worker failures. The third goal is long duration. We run these jobs that last for days to avoid any potential out-of-memory issues that might be due to the accumulation of state. So in this set of experiments, we run these workloads at different priorities, at different scales, and with different numbers of workers. During the execution, these jobs actually encounter up to thousands of worker preemptions and 100 plus PS preemptions. And the cluster and the job were able to make continuous training progress during the entire process without hanging failures or any other issues. So making the training process fault tolerant allows us to run large-scale jobs on preemptible resources. According to the Google resource pricing on Borg, using preemptible resources, especially at batch priority, can reduce 50 to 85% of resource cost compared to using dedicated, highly available resources. And thus, supporting preemptible resources is actually crucial for large-scale production jobs. Here we take the TFX Flux Canary job as an example. We have this table showing the resource cost reduction used in this production deployment. We have the column in the middle showing the amount and the priority of resources and their normalized cost when using dedicated resources, and the column on the right showing the resource and normalized cost when using the preemptible resources. And for this specific job, which typically lasts about 4 hours, using preemptible resources can save Google over 1,000 GCU hours per run and over 60% resource cost reduction. And finally, we will talk about the multi-worker testing framework that we set up. So the motivation for this work is that TensorFlow previously did not have an automated multi-worker testing environment on board. And in the V1 estimator world, we heavily relied on users or other teams, such as TFX, to report regressions or breakages. And then we just directly jumped into the users' models to debug those problems. And this was not a very productive setup. So the goal of this framework is to continuously monitor the fault tolerance and performance of PS strategy on a set of standardized models and serve as a first line of defense for any potential breakages or regressions. The architecture of the testing framework is like this. We first set up a standard guitar workflow, which gets triggered automatically to run on a schedule, such as every few hours. And then the guitar job can start a separate sandbox cluster on board, where we actually launch our TensorFlow server instances. We use a job inside guitar as a coordinator, and it can schedule and coordinate different model functions to run in the cluster. We also run a job continuously to inject failures, which can simulate the Borg preemptions, so that we can ensure the fault tolerance mechanism is functioning properly. And finally, the coordinator reports the benchmark results to the MLCompass dashboard for us to visualize and monitor the results. Currently, this multi-worker testing environment runs the MNIST, ResNet, and recommendation models continuously on small to medium scale clusters. So here is a sample plotting for some recent statistics of job completion time with and without introducing these failures. We will also be working on expanding the test scope to include more machine learning models running on large-scale clusters and low-priority resources. All right, so we went through all the content. To summarize, in this talk, we introduced the parameter server strategy, which was recently made publicly available in TensorFlow 2.4 release. We discussed the design decisions of using a single client approach and explained the programming model with a schedule join non-blocking APIs, and talked about the process of training and evaluating the model and using the sharded variables with the PS strategy. We then further explained how the TF2 eager runtime is backing up the PS strategy with distributed multi-device function execution. We discussed the performance issues we encountered and demonstrated that we can match or exceed estimator's performance with the new PS strategy. We also did a lot of scalability and fault tolerance stress testing to make sure that the PS strategy can run at large scale with low priority resources. And we also developed this multi-worker testing framework to ensure the healthiness of our product. So with that, thank you for your attention, and we're happy to take any questions.